Welcome to the Chapter 6, Part 2 video. We are going to do a quick review of simplifying radicals and then look at multiplying, dividing, and rationalizing radical expressions. So try this really quickly. This is simplifying radicals, very similar to what we did in class. And then I'll show you the answer. Okay, so just like we saw in class, we need to factor. I'm separating and looking at the numbers or the coefficients separately from the variables, circling groups of 3 because this is a cube root. The groups can escape the radical. Anything that does not have a group is stuck within the radical, and then simplifying my 2 times x as 2x squared. If you need a little bit more time to review this, go ahead and pause the video. Next, we're going to look at multiplying radical expressions. So to multiply radical expressions, if the two radicals have the same index, so if the number in front of the radical is the same, then we can combine them into a one radical together. So just like if we had 2 squared times 3 squared, we can write that as 2 times 3 squared. Now, if we have the square root of 2 times the square root of 3, I can write that as the square root of 2 times 3. Notice they have the same index. Both of these are square roots and they combine into a square root. Same thing goes for cubing and cube roots. As long as the index is the same, we can combine them. So in our first example A here, we want to know, can we simplify the product of the radical expressions and explain why or why not? So in A, notice our indices, our indexes are different. So no, we cannot simplify because the indices, which is the plural of index, are different. Okay, how about part B? On part B, our indices are the same. So we can, yes, the indices are both 3. So we can write this as the cube root of -4 times 2, which is the cube root of -8. -8 can be written as -2 times -2 times -2. And so we have the cube root of -8 equals -2. So yes, we could simplify it, and it simplifies to -2. I'm going to have you try a couple after I show you one more example. So what is the simplest form of, here we have two radicals multiplied together. And the first thing I'm going to check is that they have the same index for both radicals. Each radical has the same index. And so my indices are both 2, so I can simplify this. So I'm going to say 45 is 9 times 5. 9 is 3 times 3. I'm going to simplify and combine at the same time. And then I have x to the 5th. So I have 1, 2, 3, 4, 5 x's. I have 2 groups of 2. I have 3 y's. There's a group of 2. And then I have 35, which is 5 times 7. Both of those are prime, but see how I had a 5 earlier? I'm going to end up combining those. And then I have another x. There's a group of 2. And I have 4 more y's. 2 more groups of 2. So what I've done is these are all the factors of both radicands. So I'm going to do my 3, got that, times. I have 1, 2, 3 groups of x. I have 1, 2, 3 groups of y. And then I have the square root of 5 times 5 times 7. Those are my numbers that weren't circled. And there's also a y that's not circled. But notice those 5s, I've got 2 of them now, so I can pull that out front as well. So 5 times 3 times x cubed y cubed times the square root of 7y, which simplifies to 15 x cubed y cubed times the square root of 7y. Okay, now the reason I didn't multiply everything together first, which we can do, we can write this as the square root of 45 times 35 times x to the 6th times y to the 7th. Remember, if I have x to the 5th times x or x to the 1st, I add the exponents. 5 plus 1 is 6. Same thing goes for the y. I have y cubed times y to the 4th. 3 plus 4 is 7. But then I would end up multiplying 45 times 35 just to then factor it. So I kind of save a step by going directly into factoring. But if it's easier to see under one radical and then factoring, you're absolutely welcome to do that. Okay, so here I'm going to give you an example to try on your own, and then I will show you the answer. So again, what I'm doing is I'm factoring my radicands and finding any groups of 2, and I can group between radicands as well since they have the same index. So I did all the grouping I could see, and then I write it simplified, and then I check, is there any more grouping I can do? And then I simplify it again as far as I can go. So our final answer should be 12x squared y squared times the square root of 5y. Go ahead and pause if you want a little bit more time to review. The next one we're going to be looking at is dividing radical expressions, and dividing radical expressions is really just a continuation from multiplying them. So the same rule applies. As long as I have the same index for both radicals, I can combine them into a single radical. Okay, so multiplying, they're going to multiply together. Dividing, they'll be divided. But the most important thing to check every time before you do that is that they have the same index on each radical. So in example A, they do indeed have the same index, 2 and 2. And so I can rewrite this as the square root of 18x to the 5th divided by 2x cubed. And then we can simplify. 18 divided by 2 is 9. X to the 5th divided by x cubed. If I have x to the 5th divided by x cubed, that's 1, 2, 3, 4, 5 x's divided by 3 x's, which reduce. The shortcut for that is that I subtract the exponents, so I get x squared. And then I can factor. Now those are both perfect squares, so my answer here is 3 times x, but it was a square root, and I ended up with x to the 1st power, so that should be in absolute value bars. Remember, even, odd, absolute value. In part B, we'll do the same thing, looking at the cube root now. So we say this equals the cube root of 162y to the 5th divided by 3y squared. So it will be a cube root. Does 3 go into 162? 1 plus 6 is 7, plus 2 more is 9. If I add the digits of a number and it's a multiple of 3, then 3 will go into that number evenly. That's a little bit of a shortcut. You can also try it on your calculator. 3 goes into 16 5 times with 1 left over, and 3 goes into 12 4 times. Y to the 5th divided by y squared is y cubed. 54 is 9 times 6, which is 3 times 3 times 3 times 2. And then y cubed is y times y times y. So we get 3y times the cube root of 2. Okay. So now let's take a look at one for you to practice. And I will show you the answer after you've tried it. Again, they have the same index. Always the first thing we should check. So I can write them as a fraction within the same radical, simplifying, and then simplifying the radical by factoring. Since I have an index of 2, and I end up with x to the 1st power, which is odd, even, odd, absolute value, that x has to go into absolute value bars. Pause if you'd like a little bit more time to review. And the last topic for today is rationalizing. Rationalizing means that there's no radical in any denominator and no radical has a denominator. So essentially what we want is the bottom number of any fraction to be rational. And rational means no radicals. Okay, so how do we do that? Well, if we have a fraction that has a radical in the denominator, the way to rationalize is by multiplying by 1. And how we choose that one is we're asking ourselves, what do I have to multiply the denominator by so that there's no radical anymore? And usually what that looks like is multiplying it by itself or factors that will make enough pairs to simplify the radical. So what do I mean? If I have 1 divided by the square root of 3, I'm going to use a different example than the one that's already written here. In order to make this rational, I have 3. I need 2 of them. I need one more 3. So I'm going to multiply this by the square root of 3. And it needs to be a 1, so I always have to do something divided by itself. So whatever denominator I need to multiply by, I'm going to make that my numerator as well. Then I multiply across 1 times the square root of 3 divided by the square root of 3 times the square root of 3. That was the factor I needed, so this is now just 3. No more square root. That is now rationalized. Okay. When we're rationalizing for higher roots, instead of a square root, if I need a cube root, so let's look at the same example, but if it had been a cube root, so 1 divided by the cube root of 3, I have a 3, and now I need 2 more 3s. So I need to multiply by the cube root of 3 times 3, which is 9. So I'm going to put that in my numerator as well. So now I have the cube root of 9 divided by, there's my other 2 factors of 3 that I needed. So that's just 3. Now it feels like we should be able to simplify that because we see a 9 in the numerator and a 3 in a denominator, but keep in mind that 9 is inside of a radical. So that is not a 9, it's a cube root of 9. So that would be our rationalized cube root. Let's look at one that has variables now. So I want to find the simplest form of the cube root of 5x squared divided by 12y squared z. So what I'm going to do is I'm going to use kind of the backwards property of what we just saw, and I'm going to separate this into 2 different cube roots so that I can find out what do I need in my denominator. So 12 is 4 times 3, which is 2 times 2. So what do I need? I need a 2. I need 2 3s. I have 2 y's, so I need a y. And I have 1 z, so I need 2 more factors of z. I'm going to take all of those things that I need. I need 2 times 3 times 3 times y times z squared, which is 18yz squared. Those are the factors that I need, and I'm going to multiply that in the numerator and the denominator. So now in my numerator, I have the cube root of 5 times 18, which is 90, x squared yz squared divided by, now look at my factors. The way I have it set up, right? I had 2 2's and I needed a 2. So now I have 3 2's. I had a 3 and I needed 2. So now I have a 3. I had a y squared with another y, so I have a y, and I had a z and I put 2 more, so that's z. So we end up with the cube root of 90x squared yz squared divided by 6yz. The numerator cannot simplify because remember, we couldn't simplify any cube root of 18, and there were no factors of 5, so I know that the cube root of 90 will also not simplify. It doesn't hurt to check if you wanted to. Times 3 and 2 times 5, I have no groups of 3. And that's our final answer for rationalizing with variables. Okay. It's going to take some practice to get used to this. We'll have plenty of time to practice in class, but I do want you to have an opportunity to practice on your own. So right now I have the lesson check does not involve rationalizing, but think about it. Make sure you understand that last example, and we'll do some in class together. Do all 6 problems for your lesson check for the slides practice and upload it to Blackboard, and I will see you in class.